Hello, I'm Diptanshu Sikdar.
Hello, I'm Alvin.
Hello, I'm Saadhvi Raghav.
Hi, my name is Ian.
We're QuantumQuad, and we have been researching and implementing the NEQR and quantum steganography algorithms during these past 2 weeks, and we'd love to share what we learned in our experiences.
Our initial goal with this project was to be able to do steganography. Now, steganography is concerned with the hiding of information inside other information. For example, here we hide a message inside the image of the Mona Lisa by slightly changing the pixel values. But to be able to do that, we need to be able to do digital image processing. Now, the thing about doing digital image processing on classical computers is that images are big, so classical computers need time to process them. But this presents an opportunity for quantum computers, which can do tasks like these much more efficiently. As you can see here, classical computers use classical bits. To get multiple results, you have to do multiple calculations because classical bits can only be 0 or 1. But quantum bits, on the other hand, can be in multiple states at once. So with one calculation, you can get many results. Therefore, effectively performing multiple calculations at once. This makes a lot of tasks a lot more efficient on quantum computers, one of those tasks being image processing.
The topic we wanted to focus on was steganography, so we decided to break the problem down. Since image processing plays a huge role in steganography, we decided to first look at NEQR, or Novel Enhanced Quantum Representation of Digital Images. NEQR provides an efficient way to process digital images using qubits, which is much faster than the classical processing algorithms we have today. NEQR is the first algorithm to use the basis states of a qubit, that is, being either purely 0 or 1, to store an image's pixel values. This makes the algorithm 100% accurate. The goal is to process a classical digital image, and the input is a 2D array of classical bits, where the bits represent the intensity or the color of the pixel. The output is a quantum image. The algorithm has two registers, or groups of qubits, a position register and an intensity register. For an example, let's say we're trying to process this 2x2 image here you see on the right. We'll start with the bottom left pixel. Looking at the diagram, we know that the position of that pixel is 0, 1, so the index register or position register will be in that state. We know that the number 200 represents the color or intensity of that shade of gray, so the intensity register will represent 200 in binary. The two registers are connected in the sense that anytime we look for the 0, 1 location, we will always get the correct pixel intensity of 200. This is a principle called entanglement. This process is repeated for every pixel until the entire image is processed.
In our approach, we first implemented the NEQR algorithm in Qiskit. Then we generalized our program to an n-by-n grayscale image. Next, we assessed the practicality of NEQR, and we finally explored its application in quantum steganography. Now let's see the practicality assessment. For an n by n size image with pixel values ranging from 0 to p-1, the total number of qubits used would follow this expression. The ceiling of the logarithm of p to the base 2 number of qubits for pixel intensity and 2 times the ceiling of the logarithm of n to the base 2 for pixel position. As you can see in the table, for a 2x2 image, the depth of the circuit, which is the total number of quantum gates in the critical path, is 22. The compile time of the circuit takes about 1.8 milliseconds, and the accuracy of the circuit run on IBM's AIR simulator reached up to 99%. We also tested our circuit on the fake Montreal quantum computer, which simulates 27 qubits with a typical error rate. The red circled spikes are the correctly encoded pixel values, and the rest of them are noise. Overall, 10 qubits is the minimum for NEQR, and it can run on a quantum computer.
I'll talk a bit about the applications of NEQR. The NEQR circuit can function as a general quantum key value mapping. We have applied NEQR to quantum image processing, more specifically steganography, where data is secretly embedded within an image. Classically, this information embedding process involves tinkering with the RGB pixel values of the secret image and the cover image in order to combine the two and create a key. Using NEQR, along with some other auxiliary functions, enables an exponential reduction in both image size and the calculations made. There is much to learn from our experience implementing NEQR and steganography procedures. Firstly, while the quantum algorithm gives an advantage in processing the image, preparing the NEQR representation is still NP-hard. Secondly, the whole image embedding procedure used upwards of 90 qubits. which is more than the most advanced quantum computer today. However, given that the hardware improves in the future, quantum algorithms like this have enormous upside. To conclude, we would like to thank all the people that made this possible. Thank you to our instructors as well as our teaching assistant for teaching us the basics of quantum software. Thank you to Mr. Bob Shin, Mr. Joel Grimm, and Ms. Lisa Kelly for providing us with this opportunity.